This is going to be a quick video just sharing a really small program I made which generates a 5 limit lattice and then uses it to work out the ratios for a just intonated version of a chromatic scale, pretty much. It would be the just intonated version of each of these. So 0 to 11 could be like, C to B, or however you want to think of it. Whatever key you would want to apply it to, 0 would be the root note, and then 1, 2, 3, 4, 5, 6, so on would be the rest of the 12 tones in the system. So if you're not sure what a lattice is or ratios or what is this, I'll put a link in the description to a video I've made previously which talks a bit about it, but you might be better off in that video looking in the description, and there's a few videos which made by people that know more about it than me and are better at explaining it. So I'd recommend checking those out if you're not sure. But the reason this made sense to do for me is because there's not a lot out there saying necessarily why things are the way they are. There's a bit, there's a lot of info, and it seems to be widely accepted that, say, like a perfect fifth is 3 to 2 and things like that, but not so much really breaking down why and showing how it can be worked out without too much trouble. So I'll show you running the program now, just to show you it algorithmically generates it. It's not written in there already. There's a few things which it takes as a given, which is, say, we're going to be using a 5 limit system, which means we're just basically using primes 2, 3, and 5 to generate the ratios, which in actual pitch terms, if you multiply a frequency by 2, you get 1 octave up. If you multiply a frequency by 3, you get an octave and a fifth, a just intonated version, not equal temperament. And if you multiply a frequency by 5, you get up 2 octaves and a major third, just intonated. Equal temperament is a way where pitch is divided up, so we have 12 tones and it's static, and it's very useful because you can play in any key and you can play different kinds of chords and things like that. You can basically, because you can modulate and you can change key and you don't need to retune all the notes. But just intonation is a tuning system which is relative to a given root note, pretty much. So it means you can't modulate, otherwise it would be out of tune without you retuning the notes. But they are perfectly in tune according to basically the way the waves work. And it's the easiest way to express a just intonated interval is with ratios. So if I run this, we'll see what you get is a 5 limit lattice. This is the 12 tones of the 12 system, 0 through 11, which could be any key, doesn't really matter. If you wanted it in the key of C, 0 would obviously be C and 11 would be B. And this is how it would look on the lattice. So usually a 5 limit lattice like this, moving from here to here, is basically like going up a perfect fifth. And moving from here to here is basically like moving up a major third. And using those two intervals, you can jump around and eventually reach any note in a 12-note system. We set this one always as 0, as the root note, as the home, whatever you want to call it, as Sa, because if you start here and use this as a starting point, using those steps of major thirds and fifths, you will end up with the correct ratios. If you were to try and work out, okay, the ratio from 1 here to 10 there, and just keep repeatedly applying fifths, you end up with something that's a different ratio than if you did that by mixing in thirds as well. That's because if you keep stacking fifths, it's a different kind of tuning than if you do it by thirds mixed in as well to reach the same destination. So that's why we start at this point. That's where they're built. So pretty much what's happening is, if we take a fairly approachable one, which would be the perfect fifth, perfect fifth being 7 semitones in an equal temperament system. Essentially, you'll be multiplying the frequency of your root note by 3, and what that would give you is up 1 octave and a just intonated fifth. Now, because that's over an octave, to balance it out and bring it closer, an octave adjust it, you'd essentially bring the lower of the two notes, the root note, up 1 octave. So now you're left with a fifth. So that's why this 2 is here rather than 3 to 1. Because 3 to 1 would be an octave and a fifth, and 3 to 2 is just a fifth, just a just intonated fifth. So we're mixing in octave adjustment here. So the way it's essentially working is looking at the steps horizontally and vertically in the lattice, and then just repeatedly applying it. So for every horizontal step, if it's going to the right, it'll be multiplying by 3. If it's going to the left, it'll basically be dividing by 3. And if it's going up, that's pretty much multiplying by 5. Or if it's going down, it's pretty much dividing by 5. And once that's through, it's octave adjusting by multiplying the sides by 2 to reach a point where they're within 1 octave. It's not going over octaves. So it's quite a short program. If you're interested in this kind of stuff, you may find it interesting just to see the logic on how ratios and lattices actually relate to one another. They're not just arbitrary things. It's kind of like a proof in a way. There's probably a better, more efficient way to do this multiplicatively rather than iteratively the way I have done, but this way seems easiest for me to imagine because it's more like actually doing the steps on an instrument or something. So if this is something that interests you, I would say you can take a look at this. I'll put a link to this GitHub repo in the description here, and you can play around with it and see what you make of it. Thanks for watching.